In this lecture, we will discuss triple integration. So, triple integration. In previous lecture, we have discussed about the double integration. So, in double integration, we calculate the area. In triple integration, we calculate the volume. Okay, but we have solved some problems related to the Cartesian coordinate, spherical coordinate, cylindrical coordinate, and triple integration. So, we just understand how to use the coordinate axis in triple integration. So, this is origin. And we assume that this is our y-axis and here is the x-axis and this is z-axis. Okay, so we take a point P. So this is the point P and the point P we taken as in this form. So here we use this coordinate as PQ. So the coordinate of point P we write down as x, y, z. So this represents the plane. So we take a point P. So you can understand that that means when we take a PQ, PQ lie in the which plane? So PQ lie in the z coordinate. That means, and similarly, uh, you can say that this is we can consider as R, QR, and next we consider as S. So QS, QR and QS. So QR and QS lie on x-axis and y-axis. Okay. So QS is the x coordinate and QR is the y coordinate. So basically we take the triple integration. So triple integration to let fx, y, z. So we have three variables. Be the function over the region V, over the region V. So this we denoted as triple integration over the region V, function of x, y, z into dv. Okay, so what is the value of dv here? So that means when we are discussing about the triple integration, that means taking three axes. So we take the small strip, okay, whose length, width, and height is we consider as dx, dy, dz. So the value of this is dx, dy into dz. So dv is always we can represent it as dx, dy, dz in the triple integration. So we can write down as f of x, y, z, dx, dy into dz. So this is we are going to calculate the region that means in the given boundaries for the particular v. Okay, so v the region. Now, when we solve the problems related to that, so for solving the problems, first we start with the limits. So when all limits are constants, so all limits are constant. Suppose we are considering here x equal to a to b, y is equal to c to d, and z is equal to e to f. F of x, y, z, dx, dy, and dz. So here all limits are constant, so we can integrate any one of them first. So basically we start from z, then y, or then x. So this can be written as first we write down as x a to b, then y equal to c to d, and first we integrate with respect to z. So e to f, f of x, y, z into dz. Or here we write down as dx into dy. So first we integrate with respect to z, then we integrate with respect to y, then with respect to x. Okay. Now, we talk about the variable limits. So when one limit is variable and two are constant. So we see that sometimes one limit is variable, okay, and two are constant. So first we solve always the variable limit. So suppose we are considering here, so the situation may be occur in this form: x equal to a to b, y equal to c to d, and z limit is variable in form of y, okay, in form of y. So f1 y2 f2 y of function of x y z dx dy and dz. So in this case, first we solve with respect to y. The first we solve variable limit. So first we solve variable limit. So first we solve the variable limit, then we solve the constant limit. So constant limit, we have the same rule. That means we can integrate with respect to y, then we can integrate with respect to x. So you can write down this as x is equal to a to b and y is equal to c to d, and the limits of z is f1y to f2y f of x y z into dz or dx into dy. Okay, so this is the one case. Now we have make a different cases are there. So for different cases means, so here we see that we have taken the limit of z in terms of y. It may be possible the limits will be given in terms of x. Okay, so this may be also possible. So we can accordingly we integrate with respect to z. So we focus which variable have the variable limits. So we integrate first with respect to first. Okay, so basically we solve first variable limit, then we solve the constant limits. So hope maybe z have the constant limit, y have the variable limit. The limit of y in terms of maybe x or in terms of maybe z. Similarly, for x, maybe x have the variable limit in terms of y in terms of z. Okay, so we solve accordingly. So first we solve the variable limit, then we solve the constant limit. Okay, now next case will occur. That means when two limits are variable. So when two limits are variable. So when two limits are variable, so such type of cases that we will discuss here. So suppose x limit is constant, y limit is variable in terms of x. So we write down as f1x to f2x, and z limit is also variable in terms of xy. This may be also possible. So we write down as f of xy and f of xyz or dx dy dz. Okay, so z is limit is variable in x and y. The first we solve with respect to z because both variables we have using x and y in the limits. So first we solve with respect to z. So we write down as y equal to f1x to f2x. So first we integrate with respect to z. So f1 of xy or into f2 of xy. So f of xyz into dz, or here we have dx into dy. So when we solve with respect to z first, then we solve with respect to y because y is also variable limit. Y have also variable limit, so then we solve with respect to y, then we solve with respect to x. Okay, so hope you understand. After solving this, so then we solve with respect to y, then we solve with respect to x. So we take some problems related to triple integration. So now for special cases we will discuss later on. Integral x equal to 1 to 2, y equal to 3 to 4, and z equal to 5 to 6. X square into yz dx dy dz. So evaluate. So we are going to evaluate this integral. So we see that all limits are constant. So when all limits are constant, so then we can integrate any one of them first. So we start with z. So first we integrate with respect to z. So now, so when we integrate with respect to z, so we write down as 3 to 4. So the function is given in the product. So when function is given to the product, so we take x square into y from outside the integral. So we write down z equal to 5 to z equal to 6, or z into dz, and dx into dy. So the integration of this is z square upon 2. So we have limit 5 to 6. So you can write down as x equal to 1 to 2, y equal to 3 to 4, x square y, and when we put a z equal to 6, so 6 is 36. 36 minus 5, 5 is 25 upon 2, and dx into dy. So this gives us 36 minus 25. So 11 upon 2. So we take 11 upon 2 outside from the integral. We write down x equal to 1 to x equal to 2 into x square. Then we integrate with respect to y. So we write down as y equal to 3 to y equal to 4, y into dy. So here we write down as dx. So this gives us 11 upon 2. So x equal to 1 to 2 x square, and integration of y we write down as y square upon 2. Put the limit as 3 to 4 into dx. So this we can write down as 11 upon 2 x equal to 1 to 2 x square. So 4 4 is 16, 16 minus 3 3 is 9 upon 2 into dx. So 16 minus 9, 7 upon 2. So again we take 7 upon 2 outside from the integral. So this gives us 11 upon 2 into 7 upon 2, and we have x is equal to 1 to 2 x square into dx. So when we integrate it with respect to x, so this gives us x cube upon 3, and we take as limit as 1 to 2. So this can be written as 77 upon 4 into 2 to the 4 to the 8. 8 minus 1 upon 3. So gives us 7 upon 3. So 77 into 7 of 4 3 is 12. So this is our answer. So you are 539 upon 12. So this is the answer. Okay, so just when we have all limits are constant, so we can integrate any one of them first. Now we move to the next problem. So the next problem is push. Evaluate 0 to 1, y equal to 1 to 2, z equal to 0 to x. X square y plus z into dx dy dz. So here we see that the variable limit is for x, z. So in terms of x, so we first integrate with respect to z. So now we solve this by taking limit as x equal to 0 to 1, y equal to 1 to 2. Then we integrate first with respect to z. So x square into y plus z. So here plus sign is given. So we integrate this one. So now we write down as x equal to 0 to 1, y equal to 1 to 2. So integrate with respect to z. So first term x square into y is purely constant. So when we have dz integration is z, or plus z integration is z square upon 2. Take as 0 to x and to dx into dy. So we write down as x equal to 0 to 1, y equal to 1 to 2. When we put z equal to x, so this gives us x cube y plus x square upon 2. Or when we put z equal to 0, so gives us 0. So we do not write. Now we see that both limits are constant. So when we can integrate any one of them first. So here we integrate with respect to y. When you integrate this with respect to y, so you can write down. So y is equal to 1 to 2 x cube y plus x square upon 2 into dy. Or here we write down as dx. So this can be written as x equal to 0 to 1. So when we integrate with respect to y, so this gives us x cube into y square upon 2 or plus x square upon 2 treated as constant. So dy integration is y, and take the limit as 1 to 2 and write down as dx. So apply the limit 0 to 1. So when we put y equal to 2, so 2 to the 4. So this gives us 4x cube upon 2 and plus 2x square upon 2 minus lower limit. So this gives us x cube upon 2 or minus x square upon 2 into dx. So here 2 to 2 cancelled, or 2 to the 4. So we simplify this. So this we can write on x equal to 0 to 1. So this having 2x cube minus x cube upon 2. So 2 to the 4, 4 minus 1. 4 minus 1 means 3 by 2 into x cube. So 3 by 2 into x cube, or you have x square or minus x square by 2. So this gives us plus x square by 2 into dx. Now we integrate this with respect to x. So x cube integration is x4 upon 4. X square integration is x cube upon 3. 3 into 2, 6. 0 to 1. So we apply the limit. So 3 by 2 into, when we put 1, so 1 by 4, or plus here 1 by 6. Or when we put 0, so minus 0 and minus 0. Okay, so we write down as lower limit minus 0, minus 0. So first term is a 3 by 8, or second term is 1 by 6. So we take as 24 as LCM. So 8 3 are 24, so 3 3 are 9, or 6 4 are 24. So this gives us 13 upon 24.